Next, we have one of the most well-written texts in all of mathematics literature. It's the text by Silverman and Tate, Rational Points on Elliptic Curves. Very, very famous undergrad book for something related to algebraic geometry. And of course, elliptic curve theory. So, the first chapter covers geometry and arithmetic, points of finite order, the group of rational points. Then we go to cubic curves over finite fields, integer points on cubic curves, complex multiplication, and an appendix on projective geometry. As you see here in deduction, we start with Fermat's last theorem as motivation. And they basically try to motivate stuff like why we would care about rational points on a curve, rational points on a cubic curve or a conic curve. It establishes the group law and how we can find more rational points if we have some rational points, and basically the structure of that group. So extremely beautiful, well-written book, absolutely worthwhile to read. Even if you're not in algebraic geometry, I think this might be something that I think everybody will enjoy. This book is something that everybody will get something out of, at least to see what the field is about. For Crimson, this is especially recommended. I think he liked this book a lot. I think might be something that, he would like very much. So highly recommended to him and basically to everybody seeing this. Next, we have a book on quantum theory, a mathematical approach by Peter Bongaerts. So it covers quantum mechanics from quite a rigorous perspective. So let's see if I can find the table of contents. So here we start with introduction, classical mechanics. Then we go to quantum theory general principles, quantum theory for a single particle, harmonic oscillator, then the hydrogen atom, spin atomic structure, many particle systems, review of classical statistical physics, quantum statistical physics, physical theories of algebraic systems, quantization, scattering theory, towards relativistic quantum theory, quantum field theory and particle physics, concluding remarks. Then in part 2 we have topology, measure and integral, manifolds, function analysis Hilbert space. We have probability theory, tensor products, Lie groups and Lie algebras, generalized functions, the bracket formalism, algebras, states and representations, including C-star algebras. So yeah, it's meant for mathematicians. It's meant as a very rigorous point of view of quantum mechanics and classical mechanics. So yeah. It's definitely meant for mathematicians and for people wanting to see the structure and the foundations of the entire thing and want quantum mechanics done rigorously as opposed to what the usual physics books do. So in a sense, it is quite similar to Hall's book, but I think this one goes a bit more farther than Hall, because I think it covers different stuff, I guess. So yeah, very nice book. If you're into mathematics and want to see quantum theory, definitely worth doing. Next, we have a book by Rotman, The Theory of Groups, Introduction. So it is a group theory book. Rotman has basically books on a lot of themes, including group theory. So we start with groups and homomorphisms, the isomorphism theorems, permutation groups, finite direct products, the Silov theorems, normal and subnormal theory series, extensions, some simple groups, infinite abelian groups, homological algebra, free groups and free products, the word problem, and then some appendices. So yeah, this goes very deep into group theory and into basically everything to do with the theory of groups, including stuff like homological algebra of groups, and simplicity theory of simple groups, and so on. So yeah, personally, I really like group theory. I think it's my favorite part of algebra. So I think this book is perfect for me because it does a lot of very non-trivial stuff that you won't really find in many other books. Even the Luffy's book is not this extensive. So yeah, if you're interested in basically group theory and very advanced group theory, then this is basically the book that you will want. Next we have a very famous book. It's Lie, Introduction to Smooth Manifolds, but be aware, this is the first edition. Also have the second edition, so this comes later. So the first edition. So it starts with smooth manifolds, smooth maps, tangent vectors, then vector fields, vector bundles, cotangent bundles, submersions, immersions, and embeddings, submanifolds, Lie group actions, embedding and approximation theorems, tensors, differential forms, orientations, integrational manifolds, the Ram cohomology, the Ram theorem, integral curves and flows, Lie derivatives, integral manifolds and foliations, Lie groups and their Lie algebras. So as you can see, if you're familiar with the second edition, that the ordering of the book has changed quite a bit. Very different from what the second edition, what the first edition is. And yeah, I think the changes he made is for the better. For example, if you look at the table of contents, you see stuff like integral curves and flows coming very late after the Ram theorem. I think that's kind of a mistake. Lie derivatives also should probably come sooner. So yeah, overall, not much of the content seems to change. There seems to be changes like he emphasizes manifolds with boundaries more. The exercises almost didn't change at all. Some material has been added basically, some reworked, but overall it's, yeah, whether you go into the first edition or the second edition, it doesn't really matter that much. I think the second edition makes a bit more sense because the ordering is better. And some typos have been, especially in the exercises, some typos in exercises have been corrected. So that's why I would probably recommend the second edition. Even though, as you can see, he uses here the notation F star, while I prefer that notation very much over what he has in the second edition. It is DF, and I don't like that notation at all. I'm not sure why he changed the F star bit. Maybe because he wants it to be more in line with ordinary calculus, but yeah, I'm not sure. Overall, I worked through both the first and second edition, and I kind of enjoyed both books. So yeah, I think this is absolutely my favorite book on differential geometry, at least the smooth part of it. It is also a Riemannian part. Oh yeah, that's another difference. Riemannian metrics don't really have their own chapter here, and they're kind of a side thought, and I think the second edition does fix that up pretty nicely. All right. Next we have a book on Galois theory by Ian Stewart. So yeah, we start with classical algebra, the fundamental theorem of algebra, factorization of polynomials, field extensions, simple extensions, the degree of an extension, ruler and compass constructions, the idea behind Galois theory, normality and separability, counting principles, field automorphisms, the Galois correspondence, a worked example, solubility and simplicity, solution by radicals, abstract rings and fields, abstract field extensions, the general polynomial equation, finite fields, regular polyhedrons, circle division, calculating Galois groups, algebraically closed fields, transcendental numbers, and what did Galois do or know. So yeah, an entire book on Galois theory. Ian Stewart is a very famous author. So of course his book is good, even though I personally think Cox's books is better. His book on Galois theory is, I think, very comprehensive and very well written. So even though this book is pretty nice, I think, yeah, there are better books on Galois theory. So yeah. Next we have here a book on quantum physics by Scheck. So Scheck has basically a lot of books on a lot of topics. For some reason it starts with 4, I'm not sure where the other pages went. I think they didn't send it with me. So yeah, yeah, it's a very comprehensive book on quantum mechanics. But like all of other Scheck's book, I think the writing style is a bit messy. It contains a lot of stuff, a lot of very deep stuff, but I'm not sure I would really recommend this book too much because I'm not sure I like his writing style. Next we have here Classical Field Theory by Soper, Davison E. Soper. So it starts with fields and transformation laws, principle of stationary action, some general features of classical field theory, mechanics of fluids, mechanics of elastic solids, special types of solids, non-relativistic approximation, electromagnetic fields, further general properties of field theories, electromagnetically polarized materials, gravity, momentum conservation in general relativity, and dissipative processes. So yeah, the book is actually very hard. The exercises in here are very hard, I think, at least for me. And the writing, yeah, I'm not sure it is the clearest possible. It makes sense. It's probably a grad book, so it makes sense. It's supposed to be hard. But yeah, I think there are probably better books on classical field theory that are maybe less difficult. Next we have this one. Chris Doran and Lesson B, Geometric Algebra for Physicists. So it basically tries to do physics together with geometric algebra. So we have geometric algebra in 2 and 3 dimensions. We have classical dynamics, foundations of geometric algebra, relativity and spacetime, geometric calculus, classical electrodynamics, quantum theory and spinors, multi-particle states and quantum entanglement, geometry, further topics in calculus and group theory, Lagrangian and Hamiltonian techniques. Then we have symmetry and gauge theory and gravitation. So it tries to basically rephrase all of physics into the language of geometric algebra. And my problem is that I probably don't agree with that. I don't really see the need in doing that. I think it's just makes things more complicated than they need to be. Safe to say I'm not a fan of geometric algebra and their entire framework. Even though there are some small successes, I think it's really not worth learning all of this stuff. And I tried to work through this book and I don't really think it's that well written, so I'm not sure I would really recommend this.